SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We have been discussing about the mineral inventory estimation, and we just got into the discussion about the parameter which is called the cutoff grade, and this cutoff grade can be calculated in a very simplistic idea can be made through this expression, that a cutoff grade is essentially a parameter which is estimated depending on the prevailing cost of the particular metal of interest which will be marketed and will give the revenue to the mineral to the mining body which is doing the mining agency, and this parameter will be used for classification into ore and waste. And it is worth remembering that this cutoff grade is also not a very sacrosanct and a very fixed parameter, which is also likely to change with the change or the development in many techno-economic parameters. So, without getting much into it, we will just have a quick look on some of the other aspects. So, from this table here we can make an idea of what exactly goes on. This cash flow is an economic parameter which is one of the major, it is a very key parameter for assessing the economic aspect of any mining industry, any operating mine or a mine company which is responsible in doing the mining activity. So, this cash flow is a thing which is depending on the average grade of the ore mined, the recovery proportion, the realizable value and the operating cost into the tons of the metal that is proposed. And here we could get some idea about what happens. Suppose we fix a cutoff grade, and let us see what happens if the cutoff grade is increased. If the cutoff, here is a hypothetical example of the cutoff grade being increased from 0.18 to 0.34, and it always happens that the grade and tonnage will always they follow an inverse kind of a relationship. So, it will always be something like this. So, tonnage is increasing in this direction and grade is increasing in this direction. So, if we increase if we think of higher and higher grade or higher and higher cutoff grade. So, let us say it is a cutoff grade. So, means if the cutoff grade is high, then the total amount that is available to us from the ore body in terms of the tonnage of the ore will be less. If we make a relaxation or go on decreasing the cutoff grade, then we have more and more amount or more and more quantity of the ore that could be classified, or more in quantity from the ore body which can be classified as ore can be mined. So, we see here the same thing, that if we increase the cutoff grade, the total tons of mine is basically decreasing from 50 to 27.2 million tons, and the average grade ore is also increasing from 0.37 to 466, because the cutoff grade is the lowest value, whereas the grade, acceptable grade, can always vary in even in wide ranges, and we can think of what is the average grade that we are mining, and that also will increase with the increasing of the cutoff grade. And also we see that the strip ratio, in case when the cutoff grade was 1, when the cutoff grade went up from 0.18 to 0.34, the strip ratio went on increasing from 1:1 to 2.68:1, means 2.68 times the amount of material could be discarded as waste if the cutoff grade is increased, which is very well understandable. And we also see that if the cutoff grade goes on increasing, the operating cost also goes on increasing in terms of whichever currency you think of as a dollar per ton, or it's rupee per ton, or lakhs of rupees per ton, whatever. So here it's going from, it's also increasing, and the total revenue earned is also increasing because we are mining higher and higher grade of material, and the operating cash flow is also increasing from 1.74 to 1.83. So this table and the values that are tabulated here gives us some idea about what exactly are the economic parameters, and which help in the feasibility analysis and the economic analysis of the ore deposit in deciding whether the ore body will be worth mining or not. So the from here we can just have a quick look on the traditional methods of the mineral inventory estimation. This diagram is just for a general look, or just to have a feel of what exactly is. So this shows a the series of drill holes which are cut or which are made through the ore body and the country rock, and if suppose this could have been the part which is on the surface, and we just get some idea about the nature of the ore body, but until and unless these series of drill holes away in space from the part where the ore body is suspected to be present, and the ore drill holes are sunk at different spatial distance away, if this happens. So this is a thinking that it's a north south striking ore body, and this is an east west section, and then it's usually once the ore body dip is somehow determined or is speculated, then the drill holes have to be made from the opposite side, from the direction from the so that the drill holes actually intersects the ore body, because from this side the drill holes will always go parallel or will not be. It's always more convenient to put the drill holes exactly in the opposite direction in which the ore body is dipping. So these traditional methods are essentially the methods we can think of methods of sections, plans or longitudinal or transverse sections, polygonal methods, triangulation method, regular grids, inverse distance weighting, contouring, which we will be seeing here. But before that, it's beyond the scope of this discussion to go into details of the drilling, but the exercise involves essentially the kind of drilling that is done in these situations is to recover the drill cores. In any drilling practice, the method of drilling which is employed is essentially the drill cores are recovered in terms of in length in cylindrical masses, which exactly mimics the drill pipe which goes deeper and recovers the core, the material from below. So the drill core in several hundreds of meters of lengths, sometimes in several hundreds of meters of drill cores are recovered in this kind of drilling process. And what generally the job of a geologist is to log the drill cores in terms of what exactly the lithology, the type of rocks that are encountered at different depths, and to make a proper documentation of what exactly are present at different depths, and that is essentially the process of the logging of the drill cores, so that from which it could be nicely documented. For example, if there is a drill core which is recovered like this, and in this particular drill core it might be that for a particular depth there could be some lithology, say for example say lithology 1, and maybe for another depth there could be lithology 2, and for a depth up to this, say for example this is the ore, and similarly it may be that there could be just a particular depth span at which the drill core has intersected an ore body. Now what has to be done is that through series of such drill holes which are made at distances away from the from a center point with an intention to intersect the ore body at greater and greater depths, and then to reconstruct the 3-dimensional geometry by stacking or by using all these drill core sections and they correlate them to understand the geometry of the ore body. A small example which is shown here means this particular ore body geometry has been reconstructed here by the drills where the drill cores were recovered and were logged in terms of what exact lithologies were encountered at what depth. And even though sometimes it is not that very straightforward, there could be many situations where there could be drill loss of the materials during the drilling, there could be subsurface structures, some brittle zone or some zone in which the cores cannot be recovered. These things are well worked out, are well understood, and the logging methods and the reconstruction of the 3-dimensional geometry is done through that process. So, this process essentially by that the subsurface and then the whatever cores are recovered from there, when it intersects the ore body, if it happens to be a discrete ore body, or it may be a situation where the ore body could only be defined by virtue of a higher concentration of a particular metal. In either of the cases, the mineralized zones in terms of thickness, depths of extension, and the along strike extensions all could be worked out and reconstructed in terms of the 3-dimensional diagrams, from which it will be easy to understand or to work out the quantity and the quality parameters, because in every drill hole wherever the ore body is encountered, the assaying is done in terms of measurement of the concentration of the metals. Suppose take a very simple example that the ore body is essentially is a horizontal, if it occurs, occurs at a great depth, but the body can be let us presume that the ore body is a perfectly horizontal ore body, and the points over here is there are 25 points here, 1 to 5, and there are 5 such profiles, and the drilling has been done and each drill has been logged, and at what depth the ore body has been encountered and with what width the ore body has been encountered is documented. Now, if we want to so the exercise could be how to find out an average grade of the particular ore body. So, this method is a method which we can think of first as a method which can be called as an included area method, where the drill holes are on the boundary of the area that is chosen, and there are 5 plus 5 10 plus 6 16 locations of the bore holes which are on the boundary of the region, and there are 9 bore holes which are in the center. If we presume that each representing about say 5 units in terms of 5 units of length, then each will be an area of 25 square meter or square whatever is. So, for example, let us say they are all spaced in 5 meter intervals. So, these are representing about each will be 25 square meter, and such 9 interior points will have an area of influence of 25 square meters each, and the holes which will be on the boundary, this 3 plus 3 plus 3 plus 3, there is 12 bore holes on this, will have exactly the half the area of influence compared to the interior points, and the ones which are the 4 corner ones will have 1/4 of the area of influence for them. So, then if we want to calculate the say for example, the grade of this particular or the average, we want to represent in terms of the average value for our global estimate. So, here the situation would be that for each for this each 9 boreholes, it will be exactly the width that is coming out if we put in terms of Wi. So, for the first, if we consider then the width that is coming out to be W into the area square, whatever is coming as I will put as area square A square. So, there will be 9 such values, 9 such points will get where it will be W A square. There will be 12. So, that means I put say into 9. Then here there will be 12 areas where the width will be multiplied by A square by 2, and there will be 9, there will be 4 such areas where the width will be multiplied by area A square by 4. And then if I will sum them up together, then I can always find out an average width. Suppose I am assigned with calculation of the average width of the ore body, then the average width of the ore body, this summed up together divided by 25 will be the average width of this ore body. And now, if I am assigned with whatever parameter, if the assay value in terms of the grade, which let us say represented as G, is known for each of these 25 points. So, then the average grade also could be exactly calculated in this formula by taking the area. So, suppose if the grade is calculated as the total width, say from the total width the volume could be calculated, and the volume multiplied with the specific gravity, the mass could be calculated, and from the mass the value that is calculated in terms of the concentration of the metal, this grade also could be calculated. So, exactly the same, applying the same method which we can demonstrate through a workout exercise. The average width of the ore body, the average grade of the ore body would be calculated, and the average grade multiplied by the total volume that we can calculate for this ore body, we can calculate what is the total amount of the metal could be present in terms of tons. So, this is just a simple variation of this method, in which it is an excluded area method, where all the bore holes are interior. So, the formula is very simple. There will be 25 bore holes, and for each bore hole the width is measured. So, we will just calculate that for each bore hole the area that is calculated and the width whatever you would have got, sum over them and divided by the total number of bore holes, we will get the average width. So, what we intended to get is the average width of the ore body, and also similarly we want to calculate an average grade. So, this average grade is contributed by the grade that is measured at every 25 points, then divided by the total number of points that we have got, is going to give us an average grade, and that is the value which will report, and then accordingly from calculation of the total mass of the ore body by multiplying the grade factor, we know how much of metal could be present, or this total ore that is calculated in terms of tons or million tons in whatever unit we might be reporting. In some such situation, this is a triangular method where there are many such points of drilling points where the ore body has been encountered, and the width of the ore body is measured, and also the grade is measured similarly, but they are not exactly in a regular graded pattern as shown before, and they could be joined by into triangles, and each triangle being represented by the average of the values that is determined at 3 apical points, and can similar way the total each volume can be calculated divided by the total number of points, and the width and the total volume of the ore body and the grade can be calculated. Sometimes also, if the drilling pattern has been such, depending on the nature of the ore body that is there, they could also be joined they could also be divided into such polygonal areas, joining the points joining the points where the drill hole is drilled, and then drawing perpendicular to that line, and several such series of such lines could be joined to divide the whole area into polygons, and each point the width of the ore body and the grade of the ore body is known, and the area of the polygons can be measured, and also the volume and the mass of the ore body can be calculated exactly the same way by taking the weighted arithmetic average of that. In some cases, if the number of data points are more and the grid, the spaces have been closely spaced, it can also be some kind of contouring algorithm can be used, where the different grades as per the choice of the grade interval, which we can classify into high grade, medium grade, low grade, and then the cutoff could be specified, and contours can be reconstructed by using standard contouring algorithms. And then the area, each of the contour intervals area is calculated, and that each segment is understood to have a single value of average width. Similarly, for the different higher and higher grade areas which are contoured, this innermost part representing the highest value, and also by the same way the volume of the ore body and the total mass could, by the simple formula that the total grade, the average grade, is the grade of individual points, where I could be n, this n number of points, I varying from 1 to n. So, like G1 V1, G2 V2, G3 V3 divided by the total volume which will be measured, total the grade into the individual volume into the grade divided by the total volume. So, that will give an average grade of this ore body. So, what exactly we intend to do is to calculate an average grade for reporting purpose. Contouring algorithms will have their own problems, because sometimes because of some analytical problems, or even in reality somewhere occurrence of some very high grade material, like it happens in case of the ore shoots. The situation is that the contouring softwares will generally be more for the aesthetic and the smooth joining of the points into the contours, but such kind of outlier values also cannot be considered, and the minimum or the maximum data that would be required for such kind of contours also sometimes remain very subjective, and it is applied in 2 dimensions. But then this also is one of the traditional method by which the average grade and the total quantity in terms of tonnage can be estimated for any ore body. So, these are the examples of the sections, what I was just showing, that if this is the plan view of the ore body that is exposed, and then this kind of the drill holes are planned on a regular pattern. These 4 profiles are shown here in terms of the drill holes, and from the reconstruction of the drill holes. So, each of the 16 drill holes are stacked or are studied together in considering the third dimension, and these kind of sections. So, they each represent a section depending on what is the depth to which the ore body has penetrated, the drill hole has penetrated, and such kind of sections can be prepared, and from which we can also calculate the total volume and of the ore body, and the SA value, the grade, and the tonnage can be calculated. So, this method is a little more improved method, which is taking into the spatial nature of the data, the spatial variation, and this is the inverse distance weighting method, and it also is applicable when we have already we are already discussing about the ore body being discretized into selective mining units or the blocks. So, for example, depending on whether if we choose a block which is the one which is designated as B here, this block, or it could be a larger block that is being chosen here, which is represented as B prime, but this point represents the center of the block, and whatever grade is assigned to this center of this block would apply for this entire block. That is how is the practice in the mining. And let us say, for example, there are many points like from G1 from G1 to G9, there are several such points where the drill hole data are available, where the grade data are available. So, we want to compute what grade should be assigned to the point, center point here, irrespective of whether it is B or B prime. So, these points are at unequal spatial space or unequal distance from the center point, which are designated as G1, G2, could be represented as D1, D2, D3, D4, D5 up to D9, and we could see that the nearest point is possibly either D4 or G4, where the D4 is the nearest distance, and the farthest could be G7. So, D7 could be the farthest distance and D4 is the shortest distance. So, the whole idea about this particular exercise is that the grade at this point of the center point of this block, selective mining unit of the block, is influenced by the values of the grade in the surrounding, and the influence will be essentially be inverse to the distance. Means the influence of point 4 G4 will be the most and the influence of point 7 will be the least, and we could see here, just for purpose of demonstration, this G1, G8, G5 and G3 have not been taken into consideration. So, it is a matter of choice, they could be taken into consideration or they may not be taken into consideration. So, here this once it is realized that the value at this center will be influenced by the values in their surrounding, and the influence will be inversely proportional to the distance, means the shorter is the distance, greater is the influence. So, we will always represent that the grade, if we say that the average grade G at the center of the block would be equal to summation I equals to 1 to n Wi Gi. So, here Wi is the weighting factor, Wi is the weight, and the Gi is the grade determined in all those locations I varying from 1 to n, 1 to, for example, in this case we are taking 5 points G2, G6, G9, G7 and G4. Their distances are similarly D9, D6, D2, D4 and D7, and then this weight is actually estimated by a method which is very easy to understand. The 1 by, because we have said that this influence, spatial influence is inversely proportional to distance. So, it will be 1 by d I raised to the power x. So, this raised to the power x could be our own choice, it could be just 1 by d, x could be 1 or x could be a whole number going to 2 or 3 and or could be a part number even going to 2.5. This possibly could be determined by a different method. So, x represents the power. So, it is 1 by d I always has to be positive power, not negative. So, 1 by d I x divided by the summation of all these terms of 1 by d I x, means it will go on like here it will be, if there are 5 points. So, if I talk of the point number, so that means if I want to calculate what will be the weight for the point number 4, the weight would be 1 by d4. Suppose we say it is a squared. So, it could be d4 square divided by 1 by d4 square plus 1 by d7 square plus 1 by d9 square plus 1 by d6 square plus 1 by d2 square. So, this is what will be the value which will be coming out as for W4. So, each of the weights from W4, W2, W6, W9 and W7 will be calculated, and then the what exactly is followed here is that the summation of all these W's, Wi should be equal to 1. So, that means we can always supplement with a small exercise. Even the grades are also given here. For example, in the point number 4 it is 0.9, and in the G7 it is 1 and G9 is 0.7. So, here each of the cases it will be 0.9. So, that means for if we calculate the grade here, then the grade at point B, if we designate as grade at point V, will be equal to W4 into 0.9 plus W2 into 0.6 or 0.5 plus W6 into 0.5 plus W9 into 0.7 plus W7 into 1. So, this because we know that this W's will be with the values of 0 to 1, and all this summation of W1, W4 plus W2 plus W6 plus W9 plus W7 will be equal to 1. So, we will get a value for this point the grade at point B, which will be something intermediate between these. The most, and we can calculate if we know the value, if we work out the values of Wy, which will be which we will do in a workout example, we will see we can always calculate the grades, and that will be assigned, that grade will be assigned to the point here. So, depending on, so if we choose a larger block size or you could choose a larger area. So, now the question that will be that will come to our mind is that what is the confine or what is the limit of distance that we are going to choose. So, this the choice of what is the spatial distance, the limit that we will be choosing while calculating this weight is not cannot be answered by very simple while discussing the simple calculation procedure. They can only be, because in any case whatever grades we are assigning here is definitely not the true grade, it is the estimated grade, and we have seen that how the situation works, that most of the time we misclassify an ore to be a waste or a waste to be an ore. Keeping that aside, we have to label a particular block as ore as a ore or waste for our mining operations to be carried out and for the ore to be exploited. So, what exact spatial distance, for example, if this is the if for example, if this is the center, then what should be the what limit I should take. So, this becomes this is a question that if this limit where I should terminate it here or here or here or go beyond. This is a issue which will be sorted out when we look into a little bit more details about the and using geostatistics, that means the nature of the spatial data into account, which we will be explaining later. So, this is one example that if we have some such lots of such blast hole data, each black points are representing blast hole, and the data has been taken from one copper in the porphyry copper deposit in British Columbia. So, here these values which are representing in the most faint shade is greater than 0.2%, 0.3%, 0.4%, and the rest of is actually the cutoff. Cutoff is 0.2%, and once we measure the values, so we can contour them, and this is one example of how it could be done. And if the areas covered under these differently shaded part as belonging to high grade and intermediate grade, and the grade exactly which is just above the cutoff grade, can be the area can be calculated, the volume and the average grade and the total quantity, this all can be calculated. So, these go under the category of the traditional method of estimation of grade and the quality or quantity parameter for the ore body, and we will continue discussing this, go on to the discussion of the use of spatial geostatistics in the coming classes. Thank you.